class. So in the last class, all of you had also drawn a bar magnet and you had represented the magnetic field lines. Okay. So just with a quick revision, I would like to know the properties of the field lines. Okay. Can anyone, okay, starting from, let's start from Veera Harshit. So Veera Harshit,
Yes, sir.
okay. Can you state the properties of the magnetic field lines?
Hello.
Yes, properties of magnetic field lines.
Yes, sir. I just disconnected. Yes, sir.
Mm.
Magnetic field line goes from North Pole to South Pole when outside the magnet, and South Pole to North Pole when inside the magnet.
Yes,
Magnetic field line appears as concentric lines, and no two lines intersect each other.
okay,
Magnetic field lines are closer to each other when they are near the magnet, but become farther from each other when they are far from the magnet.
okay,
Closeness of field lines show the strength of magnetic field.
okay. So I think you have stated almost all of them.
Yes,
Okay,
sir.
Shreyasi,
Yes, sir.
okay, is the magnetic field a scalar quantity or vector quantity?
It is a vector quantity, sir.
Okay,
It
it is
has
a
both
vector.
magnitude and direction.
Okay. Can the magnetic field lines have an origin and an end? Can the magnetic field lines originate from one point and end at another point?
Yes, sir, we can say that, sir. It originates from north and ends to south.
Ends at south or end at north only?
It is a concentric circle. It's a closed path, so it again ends at north, sir.
And starts at north also? So can we say that it has a starting point? No.
No, sir.
Okay, so the magnetic fields, they cannot originate from a point and they cannot end at a point. They form concentric circles. Manan, you joined after a very long time.
Yes, there's some connectivity issues.
So see, whatever we had done, the most important of them we had done in the last class was properties of magnetic field lines, and I hope all of you are now aware of. And with the experiment of Hans Christian Ørsted, we had concluded that the source of magnetic field or the source of magnetism is the electric current. In the last class, we had seen this experiment of Hans Christian Ørsted, where a compass needle which was placed near this wire, it showed deflections, right? So if you put the switch on like this, so if you put a compass needle near this, so the compass needle shows deflection. If you turn on the switch, the compass needle shows deflection. Here it shows in one direction, and if you put the same compass needle, so it shows deflection in the opposite direction. So that means here we had concluded that there is a magnetism because of electric current. Okay, so we can write here that current carrying conductor has magnetic field. So current carrying conductor has magnetic field around it. Now, what is the shape of the magnetic field line? since we have done about the magnetic field lines of the bar magnet, and we saw that the magnetic field lines of the bar magnet, they start from the north pole and again end at the north pole. Okay, that means there is no starting and ending point, but just they seem outside the magnet, they are moving out of north pole, entering the south pole. Inside the magnet, they are moving from south pole to north pole, and hence they are forming closed loops. So what is the shape of the magnetic field lines in the case of wire? Okay. And what would be the direction? What would be the direction of these magnetic field lines? Okay. So to understand this, again some experiment was performed, and here the direction of the magnetic field lines, it was given by Maxwell rule. So see what happened if you want to find out the direction over here. So we place a cardboard. We place a cardboard like this. And pass the wire through the card. So you can pass the wire through the cardboard, so that if we find out the direction of current, it is like this. The direction of current is from positive terminal of the battery towards the negative terminal. So this is the direction of current. So to find out the shape of the magnetic field lines, again we can do that experiment of iron powder. We can
Yes, sir.
spray some iron powder on the cardboard. So if we spray some iron powder on the cardboard, we observe that those iron powder now arrange themselves in the form of concentric circles. They are arranging themselves like this, in the form of concentric circles around the wire. Just like this. Okay. So it seems that the magnetic field lines around the wire, again, they are concentric circles. As per the properties of the magnetic field lines, they should be concentric circles. So they are making concentric circles. Okay. So the magnetic field lines, they are concentric circles near the wire. Now, if we find out the direction, okay, so the direction of these magnetic field lines, it is found out using Maxwell rule, or it is called Maxwell right hand thumb
Right
rule.
hand thumb rule.
And this is a very important rule. It's used a lot of number of times. Maxwell right hand thumb rule. It's also called as corkscrew rule or a screw rule. So how to find out using this? Using this law, you, as the name suggests, you have to use your right hand. Okay, right hand, and it's a thumb rule. So there is a role of thumb. How to find out the direction of magnetic field lines? For this, you have to you have to assume as if you are holding the current carrying conductor in your right hand. You have to assume like this, that you are holding the current carrying conductor in your right hand like this. Okay, hold it in your right hand like this, such that your thumb should point in the direction of current. If your thumb is pointing in the direction of current, then the direction of your folding fingers, like if they are folding like this, so here they are folding like this. So this is the direction of folding. Or if the current is going towards you like this, so you will fold your fingers like this. Okay. So the direction of folding fingers, it gives us the direction of magnetic field lines. Okay. So if we apply that Maxwell rule over here, if we apply the Maxwell rule to this circuit, so our thumb should point in the upward direction. Okay. And if our thumb points in the upward direction, then our folding fingers they are pointing something like this. They are pointing like this in this direction.
They are anti-clockwise, right, sir?
Yeah. They are anti-clockwise. Okay. So here, the direction of magnetic field lines, it's anti-clockwise. Now the questions in this chapter, they are going to be a lot of based on the directions. They are going to be a lot based on the directions. We'll see some of the questions which come out of this Maxwell law or Maxwell right hand. So everyone has understood this. You can find out the direction.
Yes, sir.
Okay, if you can just fold your hands like this, check out if yes, you have understood this problem or not. So in this case, your thumb should point in the upward direction. So your fingers are folding like this in the anti-clockwise direction. So this is the direction of magnetic field lines. Now see, I'm going to give before starting any question from this topic. Since it has been long, we have not done any question from this topic. Before doing, I'm giving you some ideas, something which you should know. First of all, you should know about the directions. So your directions are marked like this. This is your north, south, east, and west. Okay. If at some place, suppose if you are talked of north, south, east, west, along with vertical up and vertical down. Okay. So you also have to make that. You have to make that vertical up and vertical down. So for that, you will be drawing your diagram something like this. You can take the help of this. You can draw your diagrams to be something like this. Okay. So this is your north, south, east, west, and you have your vertical up. This is your vertical up. This is your vertical down. Okay. So it depends upon the question, which diagram you have to assume. If it doesn't involve vertical up and down, so you can take the help of this one. If it involves vertical up down, so you will take this one. Or you may need some other things like motion in a circle. If any object is moving in a circle, so motion in a circle can be represented, or if any object is moving in a circle, so it has only two directions. The circular motion has only two directions. It is either clockwise or it is anti-clockwise. And it always depends on your point of observation from where you are observing. For example, if in this circle, someone is moving like this, so this is your clockwise. This is your clockwise motion. If someone is moving like this, so this is your anti-clockwise motion. There are just two directions. If something is moving along the clock needles, as the clock needles move, then that is your clockwise motion. If something is moving against that, so that is anti-clockwise motion. And this clockwise and anti-clockwise, it depends on your direction of observation, from where you are observing. For example, the same clockwise which we are observing over here from the front, this is clockwise. But if you observe this from the back, it will be anti-clockwise. So your point of observation is also important from where you are observing. So shall we come with the questions now?
Yes, sir.
Okay, let's see a small question then from this magnetic field. Just wait. I'm giving you some questions. Okay, let's see this question. However, you have the answers over here in front of you only, but still first see the question. A current through a horizontal power line. This one. So read the question. Read the question and try to find out. A current through a horizontal power line flows in east to west direction. What is the direction of magnetic field at a point directly below it and at a point directly above it? Your north. Okay, who will answer this? Tanishka? Tanishka, can you answer?
So,
Yes, can you answer this?
I can try. Sir, I think the direction of the magnetic field is directly below it. Like, I think it's south.
It is?
South.
Okay, it is towards south. Okay,
Yes.
so this is your point. You are saying that below it, it is south. And what about point above it?
Sir, I didn't understand what they meant by at a point directly above it. Like a thumb placed at a point directly above it.
Okay, okay. Okay. A current through a horizontal power line flows in east to west. So this is your direction of current. Your current is moving in this direction east to west. This is the direction of motion. This is your current. So you have to put your current, your thumb along this direction. If you find out, so you have to put your current thumb along this direction. Okay. Then fold your fingers like this. So what is the direction of magnetic field at a point directly below it? If you observe directly below this wire, so directly below this wire, I observe over here, what will be the direction of magnetic field lines?
So will it be south?
It will be from north to south. Okay. It will be, see, this is your east to west, and if you fold your fingers like this, so below it, you are observing it to be going from north to south, and above it you are observing it to be going from south to north. This is the direction of magnetic field lines that you find. You find your field lines to be something like this. It's going like this, coming over here like this. Isn't it the direction of magnetic field lines that we find out using the
Sir,
Maxwell rule?
I understood the north to south part, but then I didn't understand the directly above it, like south to north.
Okay. Okay, so there are 2 points. Okay, a point directly below it and a point directly above it. Okay. So everyone has understood this question?
Yes, sir.
So since let's see the next one. You can see, check the answer. The current is in the east-west direction. Applying the right hand rule thumb, we get the magnetic field at any point below it. Turns clockwise in a plane perpendicular to the wire when viewed from east and anti-clockwise when viewed from the west. Uh, uh,
Instead of north to south and south to north, they have put clockwise and anti-clockwise.
yeah, so that's same thing. Okay, here is a question. Why don't 2 magnetic field lines intersect each other? Manan, Kesubha Charvik, and a few people have not turned on their camera. Please turn it on. So why don't 2 magnetic field lines intersect each other? Anyone? Kesubha Charvik will answer. So, yeah, why don't 2 magnetic field lines intersect each other? I think we had discussed this in the last class.
Last cause I not kids.
Okay. And Saryu,
Yes, sir.
why don't 2 magnetic field lines intersect each other?
So because they are concentric.
Certainly not a correct answer.
So may
Mehak?
I?
Okay, let Mehak answer. Mehak?
So maybe because they don't have a starting point.
Okay.
Can I say so?
Yes, Vedika?
Sir, it was chassis.
Okay, Shashi.
Sir, it is because, sir, 2 lines, if there are 2 lines, if they intersect each other in a magnetic field, then the compass cannot show a proper direction because at one time and at a single place, it cannot go in 2 directions.
Yes, I think I explained this in the last class that at the same time, a magnetic compass needle cannot point in 2 different directions. At the same place and at the same time, a magnetic compass cannot point in 2 different directions. Okay, so that is why, suppose in the last class I explained it like this. Suppose this is one of the magnetic field lines, and you have another magnetic field line going like this. So suppose they are intersecting. Okay. So if the 2 magnetic field lines are intersecting, it means if you put a magnetic compass at this point, so at the same time, the compass will point along this direction, a tangent to this curve. So at the same time, the compass will point along this direction and it will also point along this direction. So is it possible for the compass to point in 2 different directions at the same time? Not possible. Okay. So no 2 magnetic field lines can ever intersect each other, because if they intersect, it would mean that the compass needle point in 2 different directions at that point. okay, which is not possible. Okay. So let's see if there is any other question. Okay, I have one question and you should solve that. Let's try to solve this if you are able to do that. Suppose if you are sitting in a room such that your back is towards the west, you are facing east. So I'm not writing, you will speak up. You are sitting in a room. You are sitting in a room such that you are facing in the east direction and a beam of protons are entering the room. They are entering towards you. So what should be the direction of magnetic field lines?
Sir, east to west.
You are sitting east to west.
So from north to south.
Okay, let's see.
Sir, you
Yes.
told that the protons are coming towards us.
Yeah, the protons are coming towards you. Take a minute if you can answer it correctly, but your answer should be correct. Take a minute. You are sitting in your room facing towards east. Your face is towards east.
Sir, in what way should we give the answer, sir? Like above us and below us, like that?
No, you are observing from your point of view. That's what I say. You are facing east. Okay. And the current is moving, coming in front. The protons, they are moving like this. This is the direction of motion of protons. So how you will observe the magnetic field lines to be?
Clockwise, sir.
Sir, north to south.
Hmm?
North to south.
North to south.
North to south.
The
Okay.
south
Yes,
to north,
sir.
sir. Clockwise.
You will observe them in circular shape. Yeah, you will observe the magnetic field lines in the form of circle.
Yes, sir.
Okay. So should it be clockwise or anti-clockwise?
Sir, I think it should be anti-clockwise, right?
Sir,
Okay. Yes.
clockwise, no, sir.
Clockwise, sir.
Clockwise.
Sir, clockwise because, sir, the hand thumb rule, sir, it's pointing behind us, sir. And because if we move our hand, sir, it goes from down south to north, no, sir. Because like clockwise is that way, sir.
See, every question is important. Take a minute, think of it. Suppose I am sitting over here, okay, and I am facing towards east. The protons are coming towards me. So this is the direction of current. Now I want to find out the magnetic field. So I will point my thumb towards me. Thumb point towards me, and
It
my
should be
Sir, it
fingers
would
are
be
anti-clockwise, sir.
anti-clockwise.
okay. So my fingers are curling. Now the curl of fingers is clockwise or anti-clockwise. You observe it on your own.
Anti-clockwise, sir.
Anti-clockwise.
Yes, sir.
If you have doubt, just take a minute, think of on your face, just make current is coming like this and move it. See, it's anti-clockwise. Okay. So you will find here that the direction of magnetic field is anti-clockwise in this question. Okay. Any other doubt? Now we shall move towards the next topic, that is magnetic field due to a current carrying circular loop. Next
Sir,
topic.
can you explain how is it anti-clockwise, sir?
Okay, in your room, who is asking this?
Sir, Shasi, sir.
Okay, Shreyasi, in your room, just turn your face towards east.
Sir, I am sitting towards east, sir.
Okay, and suppose the current is coming towards you.
Yes, sir.
Okay, so your thumb should point toward you.
Yes, sir. Yes, sir.
Okay, so your fingers are curling. If you see the fingers curl, the curl of fingers you see in which direction? Do you see them in clockwise or anti-clockwise?
Okay, sir. Yes, sir. Anti-clockwise, sir. I was using left hand, sir, the whole time.
Okay, so if you are using right hand, you have to use your right hand. This will happen. You will get tired with one of your hand, so you will start using the next hand. The next is magnetic field due to a circular loop. So here we take a circular loop. Okay. Uh, Monish. So let's take a circular loop. Mm. So here we take a circular loop. Let this be the positive terminal. Let this be negative terminal. So you will have current flowing through this loop like this. Right? Now you will tell me what will be the direction of magnetic field at each point where I am asking. Okay. Again, we are going to use the same Maxwell rule, but for different points. Let us say I'm considering in the first case, I consider in the first case, I consider this length of the wire. Then here I consider this length of the wire. Here I consider this length of wire. And here I consider this length of the wire. Okay. So if you just assume this much of length, okay. So what will be the direction of magnetic field line at this point and at this point? At this point, how you will observe? Are the magnetic field lines coming out of the board or they are entering the board? At the point above this. At this point. Use your Maxwell rule. I have marked the length. You have observed just for this length, the current is moving like this. This is the direction of current. Okay. So direction of current is like this. And if you move your fingers inside it, so outside this circle, you will observe that your fingers are moving out of the board. They are
Sir,
coming out
outside
of.
is north, inside is south, no, sir.
We will see that outside north and south, that we will see later. Okay. When we describe the direction, so then we will see. So here we observe that the magnetic field lines, they are coming outward. Here we observe they are entering inward. So we can make the magnetic field lines at these points like this. I can make the magnetic field lines to be like this. Okay. Then, are you getting, is this correct?
Yes, sir.
Just check it with your thumb rule. Is it correct?
Yes, sir.
Yes, sir.
Again, if we find out over here at this point, a point inside it and a point outside it. So our thumb should point in the downward direction and curl of finger is like this. Okay. So inside the loop, you will find your magnetic field lines, they are moving out like this. Is it?
Yes, sir.
If anyone is getting something else, so please tell that no, this is wrong. Everyone is getting the same thing?
Yes, sir.
Sir.
So see, this point you have observed. Now we will take the other point, this point. And at this point, if we make the magnetic field lines, I can see a number of students have turned off their cameras. Tanishka, Veera, Harshit, Monish. Every time I should not be telling you.
Sir, I have a little bit internet issue. I'll just turn it on 2 minutes.
Okay, so you, K. Subha Charvik. Okay. For this portion of the wire, if you again observe, so your current is going like this. And again, if you observe, so inside the loop, at a point inside the loop here, and at a point outside the loop, so you will observe that the magnetic field lines, they are moving like this, from outside to the inward. Okay. Similarly here also. So we observe the magnetic field lines are like this. So first of all, tell me that has everyone understood what is the direction of magnetic field lines at all these points?
Yes, sir.
Okay. So see, if I'm going to make these field lines a little bigger, if I'm going to make it like this, I'm going to make these magnetic field lines like this. I'm going to make these magnetic field lines this. So can I see that all the magnetic field lines, they are moving into the circle? Are all these magnetic field lines moving into the circle or not?
Yes, sir.
Okay, this one is also moving into the circle. 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 So at the center of the circle, all the magnetic field lines, they are in the same direction. This one is also entering like this one is also entering, this one is also entering. So all the magnetic field lines, they are entering at the center with the same direction, right? So at the center, the magnetic field lines, they appear to be straight lines. At the center, the same magnetic field lines, they will appear to be straight lines like this. Like this, they appear to be entering the circle in a straight line. Okay, and then from there, moving out of the circle. Okay, so how do we say? See, again, we will see this. Remember one more point. If you have a bigger circle, let me take a bigger circle over here. Okay, let's see this. Okay, this circle is big one. Okay, all of you can see a big circle.
Yes, sir.
If I cut a small length out of it, I'm cutting this much of length out of this circle. So won't this appear to be a straight line to you? Will this appear as a straight line or not?
Yes, sir. Yes, sir.
If you take a bigger circle and from that bigger circle, if you take just a small portion of it, so doesn't it appear like a straight line?
Yes, sir.
So that is why our earth is spherical, but still we see our earth to be flat, right? We see that the earth is flat because it's so big. Our earth is so big that we can take it to be flat. We can take it to small portions to be flat. We can take our field to be flat. Okay, I hope you are getting my point.
Yes, sir. Yes, sir.
Okay. Now similarly over here, if you see over here, so in this circle, as we are moving towards the center, the magnetic field lines, they are becoming big circles, and those small portions of the circle, they appear to be straight line at the center. Okay. So the magnetic field at the center is a straight line, right? Let me show you another diagram for this. If you can observe this diagram given here. Again, this is the same thing, but a clean diagram for which we have drawn.
So that one straight line is a part of a whole big circle, right, sir?
Yeah. But if you observe it, so at the center, you will observe it to be a straight line. Okay. Since this circle is behaving as a magnet, you can see that this circle is behaving as a magnet, and the magnetic field lines which move out of the circle, that is the North Pole, and from where the magnetic field lines enter, that is the South Pole. So therefore, one side of this circular loop is the South Pole, and the other side of this circular loop is the North Pole. Okay. Now I will tell you a very simple rule to identify which one is a North Pole and which one is a South Pole. So anyone has any doubt? Just make this diagram. Make this diagram. It's the same thing that we have drawn. So either you draw this one or you have understood this. So you can draw this one. I do this just to explain you. Okay, from all the sides. You need not draw from all the sides. You can draw from one of the sides, top and bottom, and then reach at the same conclusion. Try to make this diagram. Near the wire, the magnetic field lines, they are a straight line. Okay. And they are concentric circles near the wire. And towards the center, they become almost straight. So I can write here. Okay, have you drawn?
Yes, sir, done, sir.
Okay. So as you can see here, the magnetic field lines near the wire, they are concentric circles, and the magnetic field lines at the center, they are straight lines. Okay. Now, with this help, we will try to predict that which side will be a north pole and which side will be a south pole. A very simple trick is there to predict that which side of this circular wire will be a north pole and which side of this circular wire will be a south pole. So let us say again, we take these circular wires. We will see. Suppose we are observing from the front. Okay. So we are observing from the front, and let us say in this wire, the current is moving in the clockwise direction. Okay. So if you curl your fingers like this in the direction of current, so your thumb is pointing away from you. Okay. So your thumb is showing you the direction of magnetic field. The magnetic field is moving away from you, and hence what side you see, the side towards you is the south pole of the magnet, or it is the south pole of the circular ring. If you observe the current to be going in the anti-clockwise direction, then the side towards you is the north pole of north pole.
Sir,
Yes,
can you explain again?
yes, of course. See, here we are trying to use the Maxwell rule we just studied in the opposite way. Okay. What is that opposite way? In the rule, we said that the thumb points in the direction of current. Okay. Then the folding finger point in the direction of magnetic field lines. Right?
Yes, sir.
Okay. But here we are going to use it the other way. We will say that the folding fingers now point in the direction of current. Okay. Then thumb will point in the direction of magnetic field lines. So in this way also we will see. So if in this circle you see that the current is moving in the clockwise direction. So make your fingers curl in the clockwise direction like this. You observe that the magnetic field is moving inward. Okay. So magnetic field is moving towards from you into the paper. Okay. So it is moving away from you, and magnetic field, it moves away from the south pole. Okay. It's leaving you. Okay. And inside the magnet, this is the inside of magnet, and inside the magnet, that is the south pole from where the magnetic field lines leave. So this will be the south pole of the magnet, and this will be the north pole. Okay. So think of these two. We can use the Maxwell rule in both the ways. Okay. So just you need to do a little bit practice for it. I'll send you a few questions which you can practice for finding out the direction of the magnetic field lines. Okay. Bye everyone. Good night and see you all.
Yes.
Sir, thank you.
Thank you, sir. Bye.
Thank you so much, sir.
Thank you so much.
Bye.